In this video, we discuss what's called implicit differentiation. And basically, it's whenever we've got a function of y, and we want to take its derivative with respect to x. Provided that we know that y is actually a function of x. Well, if I know that y is a function of x, when I take the derivative of a function that looks like this, I just take the derivative of the outside, evaluate it at the inside, times the derivative of the inside by the chain. Or alternatively, we might write it this way: f prime evaluated at y times dy dx. So here's an example, very simple example. Let's say you have a y cubed as part of your expression, and you're trying to find the derivative of y cubed with respect to x. Then the derivative with respect to x of y cubed is just the derivative of the outside function evaluated at y. The derivative of y cubed would be 3 times the inside function squared, or in this case, our inside function is y of x. And then we multiply by the derivative of the inside, which is y prime. Or alternatively, you can just write that as 3y squared times dy dx. It's the same thing, it's just the chain rule. It's very, very simple, very easy to understand. And sometimes when people talk about implicit differentiation, they just say if the variables don't match, differentiate as usual to get your 3y squared and then multiply by y prime or multiply by dy dx. But the reason that we do that is because of the chain rule, because y actually depends on x, and we're putting that inside function back inside, and then we're multiplying by the derivative. Let's look at a specific example. This is actually directly from the textbook. Here I have y cubed plus y squared minus 5y minus x squared equals -4. And I might want to find the slope of the curve at some location xy. Now, typically, if I could solve for y, I would solve for y as a function of x and then find the derivative using our derivative rules. But this time I can't. I've got this cubic function involving y. We could use what's called the cubic equation. We could add this 4 to the other side and then substitute values of the coefficients into a cubic equation that's similar to the quadratic equation, and that would allow us to find y as a function of x. But it's very tedious. Rather than doing that, we're just going to find dy dx using implicit differentiation. So we're going to differentiate both sides with respect to x. And then we'll do what we just talked about. We'll say, assuming that y is a function of x, the derivative of the left-hand side is the derivative of this y cubed. With respect to x, it's going to be 3 times my inside function to the 1 less power times the derivative of the inside, which is dy dx. Then we'll add the derivative of y squared. Derivative of function squared is 2 times the function. Put your inside function back inside, and then multiply by the derivative of the inside, which is dy dx this time. Or you could use y prime, either one is fine. Then we subtract 5 times the derivative of y, which is just denoted by dy dx. And then we subtract the derivative of x squared, which is 2x. Just bring the power down, multiply by x to the 1 less power, and set that equal to the derivative of the constant on the right-hand side, which happens to be 0. Now we're trying to get dy dx by itself. We're trying to find the slope of the curve that is given by this function. we can do that relatively easily. These terms have a dy dx in common, and that 2x doesn't have any dy dx's in it. So we'll add the 2x to both sides and factor out the dy dx from this side. That dy dx times, that can be simplified to 3y squared. That's 2 times y. Then we're subtracting 5 equals 2x. And so dy dx equals 2x divided by 3y squared plus 2y minus 5. Now, one issue that we run into is domain and range issues. This is the slope of the curve at any point xy that satisfies this equation. So if I substitute an x equals 0 to this, there might only be one y value. Well, actually, if I substitute an x equals 0 to this, we're going to end up with a cubic equation set equal to 0. So that could potentially have up to 3 roots, 3 y values that cause it to be 0 at x equals 0. I mean, I might only have one y value that causes x to be 0. The other y values might be complex. Like, I really don't know unless I look at the graph. But provided that we have a point on the graph of this equation, the point that satisfies this equation, we can substitute that value in here, and this is going to give us the slope of the graph at that location. So that's how we do that. It's very, very simple. And here is our steps. We differentiate. Here are our steps with respect to x on both sides. Then you've got this, you want to remember to differentiate implicitly anytime you've got a y in your term. And then you just solve for dy dx. Or you can call that y prime if you like. You just want to get that derivative by itself. So usually we group all the terms involving dy dx on one side, move all the other terms to the other side, and then divide. Or factor out the dy dx and then divide. Okay. That's it, easy breezy. Now let's look at the curve and think about what the graph looks like. And then we can plug in some x values, xy pairs that satisfy this equation and also satisfy this equation. Now when I graph y cubed plus y squared minus 5y minus x squared equals -4, this is what the graph looks like. So if I zoom out a little bit, it appears that my y values go from whatever that minimum is to negative or to positive infinity. And the x values seem to go from negative infinity to positive infinity. So it looks like I can plug in any x values I want. And the y values have to be above y equals -4, -3 there. So our range is -4 to infinity. And our domain is positive or negative infinity to positive infinity. Now, the slope function that we found was, let's say, let's call this y prime, is equal to 2x divided by 3y squared plus 2y minus 5. I wasn't sure if the Desmos would like that. It didn't mind that I typed that in, but I guess I don't know if it knows which variable is the independent variable, which one is the dependent variable there. And because this y prime is a function of both x and y. But if I wanted to, I could pick a point that's I know to be on the graph. It looks like x equals 2, y equals 0 is on the graph. And then we could draw a tangent line there. So our derivative at that location is 2 times x divided by what we get when we substitute y equals 0, so that's -5. So we have a slope of -0.8. And our derivative or our tangent line is y equals that y value plus the slope times x minus the x value. And we get a tangent line. So this is nice and easy. The graph is tangent to the curve at that location. And that point is on the graph. Now it's a little bit harder to come up with a slider, an X value that can move around when this is not in function notation. But we could, if we wanted to, say, okay, let's let our X value equal some function of Y, or and that's actually possible in this case. It's not easy to find Y as a function of X using this equation, but we can find X as a function of Y. So we saw a specific example when that point on the graph was obvious, but you're like, okay, but what if the point in the graph isn't obvious? Well, I can solve for X by adding 4 to both sides and then taking the square root. And actually, let's do that on paper. You have y cubed plus y squared minus 5y, add 4 to both sides, add x squared to both sides. We have x squared is equal to this number. So x is equal to plus or minus the square root of that expression. So x can be positive or negative. It's going to be 0 whenever this cubic function is equal to 0. And then we take the square root of this. We're going to have positive values for one of the functions. And I think that's where we see this kind of weird thing. And then negative values on the other side. And there's some symmetry. So I usually call this the top function. And this one the bottom function. Or if you want, you can call this x right and x left. This one's x right. And then this one on the other side is x left. But the x values are larger over here on the right. So that's where we have the positive square root. And then the x values are negative on the left. Okay. Now, if I graph that sort of top function and bottom function, or left function and right function on Desmos.com, the positive square root corresponds to the right half. The negative square root corresponds to the left half. I guess I should use right and left. So I'll use right and left. Same thing. I was using top and bottom for larger values and smaller values. But we can use right and left instead. And I'll make them the same color because we're talking about a relation where you've got occasionally more one x value that maps to multiple y values. And then we have this little slider that allows us to change the point on the graph. So now we can graph x right, evaluated at y naught. So we're thinking of x as a function of y rather than having y as a function of x. And then y naught. So there's a point on the graph. I'm going to make that green. And then label it. And then we can also look at x left. At y naught. And a particular value of y. We see the symmetry. It's the same y value. We've got two x values that correspond to that y value. And then we can find the equation of the tangent line. It's just y equals y naught plus the slope times x minus x naught. And the x values are found using the functions. Just changing all those tops to right because we're talking about a function on the right. And that gives us the tangent line there at that location. And then the other location is a little bit harder. And it's a little tricky. Actually, not going to get into these derivatives too much here. Because this video was supposed to be about implicit differentiation, and I'm getting off on a tangent there, aren't I? No pun intended. There's the other tangent line. Actually, that one doesn't quite look like it's tangent to the graph. Something that's not quite right about this. Yeah, I don't understand what's I must be making some kind of mistake. All right. Oh well, let's get rid of those. And let's get rid of those labels. But this is our function. X right and X left are the same as just the solutions of that equation. So we've got all of these points. X equals -1, Y equals 1 is on the graph, X equals 1, Y equals 1 is on the graph. We've got -2, 0 and +2, 0. We've got negative approximately 3.2 and positive 3.2. So there's a lot of symmetry, which is what we expect when we have the positive square root and the negative square root number. But we know we've got all of those points, so let's look at them. I'm going to say x, y equals ±1 and 1. X, y equals ±2 and 0. And then x, y is approximately ±3.238 and -1.667. And then we've got this x value here at the bottom when x equals 0. Y is approximately equal to -3.061. And of course, we can move this point around to find points on the left and right sides of our graph. So we have these points on the graph, and we want to find the slope at each of those locations. Well, it's easy enough. At xy equals 1, 1. Just substitute in 1 and 1 for x and y here. So we get 2 times 1 over 3 times 1 squared plus 2 times 1 minus 5. Ruh-roh. I've got 2 divided by 0. So that's undefined. And then at -1, x equals -1, y equals 1. We're still going to have a negative number divided by 0. So it looks like the slope is undefined. At ±1, 1. Now let's look at the graph and see if we've got vertical tangent lines there. Because if I have a non-zero number divided by 0 in the limit, as that denominator approaches 0, the limit will be approaching positive or negative infinity, and that would correspond to a vertical tangent line. So let's plot x equals 1 and x equals -1. Are those tangent to the curve at 1 and -1? I think that they are. So at those locations, we have a vertical tangent line, so that's fine. At these locations here, I would expect it looks like a slope of +1, and here I would expect a slope of -1. So let's plug in x equals ±2, y equals 0 next. If x is ±2, we've got 2 times ±2, it's going to give us ±4 in the numerator. Y is 0, this is just 0 plus 0 minus 5, which is -5. So we either get 4/5 when x is equal to +2, or -4/5 when x is equal to -2. So we could graph the tangent lines at those locations and see if we have the right slope. We'll have y equals y naught, which is 0, plus the slope, which is 4/5 or 0.8, times x minus 2 when x is 2. Oops, did I do that wrong? I get 2 over there. Looks like it should be -2. We get a positive slope. Okay, I see what I did wrong. I had plus or minus 4 divided by -5, so I should change those signs. So I have a slope of -0.8 at x equals 2. So that's our tangent line there. And a slope of positive 0.8 at x equals -2. And so that's my tangent line there. Let's get rid of these other tangent lines for a second, just to make sure that we graphed this correctly. That looks tangent to the curve. That one looks tangent to the curve, so looks like we did that correctly. That's good, good news. Okay, and were there some other values? Wrote them down. Let's see. Now these other x values, they weren't precise. That was just read from the graph, but I'm not 100% sure that those are exact answers. They might be decimal approximations. So we could plug in these the x values and the corresponding y values to this function to find the slope, but I think it's kind of a pain. I think we understand what would happen though. You just take the 2 and you multiply by the 3.238. You divide by the 3 times this number squared plus 2 times this number minus 5. You simplify. It's very tedious. Eventually you get a number. And then you use that point. And this is your x naught, y naught, and your point slope equation. You're going to find that value. This is going to be your slope. And so you have y equals y naught plus the slope times x minus x naught as the tangent. So that's the idea. Okay, so regarding implicit differentiation, how do we do this? We've got an equation involving y and x. If you can't get y by itself, you differentiate implicitly. You assume that y is a function of x somewhere. Now, y isn't always a function of x. If we look at that graph, we can tell that it's not a function of x, it's a relation. But on particular intervals of x values, it is a function, and as a function, it has a derivative. If we want to find the value of that derivative, we can differentiate this side with respect to x and this side with respect to x, and get an expression involving dy dx or y prime on one side, keep all the terms involving x to one side, all the terms involving dy dx are on the other, factor out the dy dx, and then divide to get dy dx by itself. And you get this function involving x and y. But you do have to be careful. You can't just plug in any xy pair to this equation and get out a slope. You can. You can find a value for this for any xy in the xy plane where the denominator is well defined. That's not necessarily on the graph of this function. We want points on the graph of this function because we're looking for lines that are tangent to the graph, or I said this function, this relation, excuse me. We want to find the slope of the curve that is given by this relation, and it's given by this formula. At particular points x, y that are on the curve, those are the points of interest. So be careful about that. Usually those points will be given to you in a quiz or a test. So you'll just plug in the values that are given and do what we've already done. But let's do another example of this. This is one of the simplest examples. I use it all the time. Y equals x squared, or x squared plus y squared equals 4. This is just a circle of radius 2. Kind of a standard one from my lectures. This is not a function, but we can solve for y and make y a function of x. We subtract the x squared from both sides. And then we take the square root. Don't forget your plus or minus on the right. You get 2 functions. Positive square root of x, 4 minus x squared, which is the top half of this circle. And the negative square root of 4 minus x squared, which is the bottom half of this circle. Now we can find the derivative of this function just using our differentiation rules. Or these two functions using our differentiation rules. If we have y is equal to quantity 4 minus x squared raised to the 1/2, y prime is equal to, well, we have plus or minus, and then we'll use the chain rule where this is our inside function. We'll have derivative of the outside, so it's derivative of a function raised to the 1/2 is 1/2 times the original function raised to the negative 1/2. Put the inside function back inside. And then you want to multiply by the derivative of the inside function by the chain rule. And 4 minus x squared has a derivative of 0 minus 2x. No, 0 minus 2x is, of course, just negative 2x. Negative 2 times this 1/2 is going to give us, well, it's going to have the opposite sign of whatever we have here. So if this is plus or minus 1/2 times negative 2x, we're going to have minus or plus x times that quantity 4 minus x squared raised to the negative 1/2. We can put that 1/2 power expression in the denominator. So you have minus or plus x all divided by the square root of 4 minus x squared. So we've got two derivatives. Y equals negative x divided by the square root of 4 minus x squared. This is the slope of y equals the negative square root of 4 minus x squared. Or excuse me, the positive square root of 4 minus x squared. And y prime equals a positive x over the square root of 4 minus x squared. That's going to be the derivative of y equals the negative square root of 4 minus x squared. And if you're unsure, you can always draw some tangent lines to convince yourself. In the bottom half here, when x is positive, I'm going to have a positive number divided by something that's positive, so I'll have a positive slope. So that is the graph of y equals the negative square root, because the y is negative over here in this area. Now, if y is positive, we're interested in the same x value, but up here, when we draw the tangent line, the slope is going to be negative. Going to have the same magnitude as the slope, but it's going to have the opposite sign. And that's consistent with our picture. So on where y is the positive square root, we get this as the derivative, and when y is the negative square root, we get that as the derivative. Now you might say, okay, well, what if it wasn't that easy? What if I couldn't get y by itself and I wanted to find the derivative of y with respect to x? Well, we'll use implicit differentiation. So just do that. Take the derivative of x squared with respect to x, that's 2x. And the derivative of y squared with respect to x is 2 times the inside function, which is y of x, times the derivative of the inside. And that equals the derivative of 4, which is 0. Now, if I want to get dy dx by itself, all I do is subtract the 2x from both sides. And then we divide both sides by 2y. And we end up with dy dx equals negative x divided by y. Now, if you're saying to yourself, okay, well, which points x, y can I substitute into this equation? Well, you can only substitute in those points that satisfy this equation up here. So we need y as a function of x. Well, actually, we don't need y as a function of x. If we can solve for y as a function of x, we know that y is equal to this. And we can substitute that in down here. Y is equal to plus or minus the square root of 4 minus x squared. So I take a negative and I divide by this plus or minus expression. I'm going to get a minus plus x over the square root of 4 minus x squared, which is the same thing that I got over here. And again, this is undefined when y is 0, because we have a vertical tangent line to our graph on either side at y equals 0. But as long as we substitute in these x values in the range, or excuse me, the domain of this relation between negative 2 and 2, we can find a slope that's well defined for that x value. So thinking about that technique, I know that this is dy dx for this function whenever it's well defined. So we don't want to divide by 0. And we're only interested in those points that are on the graph. But by solving for x, I can write this as a function of y only. So I'll have x equals y cubed plus y squared minus 5y plus 4. The plus or minus the square root. And so we have 2 times plus or minus this square root involving y. Is equal to, or that divided by this. That's our derivative. And if you wanted to, you could say this is the derivative of y with respect to x. It's this function of y. Rather than that, you could just take reciprocals. And you have the derivative of x with respect to y is the reciprocal of that. I know that seems like you're really allowed to do that. Like, yeah, you can. It's actually totally fine. It's legal. Now you have the slope of x as a function of y. If you can plug in a y value and the answer makes sense, then that will be the slope of the graph given by y as a function, or x as a function of y. And you can have either the x curve on the right or the x curve on the left, depending on whether you take the positive square root on the right or the negative square root, which is on the left. Okay, so we had y prime equals this. We said if we solve for x in this equation, we get 2 versions of the equation, x on the right and x on the left, which correspond to a positive square root and a negative square root respectively. So this is my x right, and this is my x left. And if I graph those, there's x right, it's just highlighted on the right side, and x left looks like that. The left and right half of this curve. Well, our derivative that we found implicitly was this. I could write that as a function of y by replacing x with either x right or x left. And then x prime of y is just the reciprocal of that. So this is dy dx, and dx dy, this is the reciprocal, and that's a function of y. So I used x prime equals this. I used the positive square root this time. And I should probably write right on here somewhere. Okay, it doesn't like that. Accidentally gave my, there it is. I don't actually want to graph it though. But there's that. And pick the y value. And then there's the tangent line at x equals y naught, or y equals y naught, and then the corresponding x value. I just used the equation of the tangent line. I modified it a little bit. I said x is the original x value plus the derivative of x with respect to y, which is change in x divided by change in y times the change in y. So change in x over change in y times the change in y is the change in x plus the original x value is the new x value. That gives us the equation of the line. We can see that there, and then we can move this little y value around. And say, okay, but what happens on the other side? Look at that point, sort of like a mirror image of that. Let's look at that one. We have x equals x left, evaluated at y naught, plus, I think it's going to be the derivative, or excuse me, the derivative of this is going to be a little different. The other x prime is going to be the opposite of that. And then we multiply by y minus y naught. And check it out, it's tangent to the curve. Okay, so we're doing a lot of graphing. I don't know how much of this is really related to implicit differentiation. But the key is when you're doing implicit differentiation, a couple things. Every time you see a function of y, when you've got an equation involving x and y and you're differentiating with respect to x, treating y as a function of x, then you have to use the chain rule whenever you see a y as a function of x. And then whenever you're using that derivative formula that you found using implicit differentiation, you have to make sure to only plug in or only substitute points that actually satisfy the equation of the original curve. And those are a little bit harder to find than you might imagine. In this particular example, we were able to find x as a function of y and sort of reframe everything by getting x as a function of y, finding the derivative of x in terms of y, using that to come up with our tangent lines, and basically treating it the way we would normally treat the function, but we're sort of treating it like that on its side, where we've got two functions, x is a right function and a left function, and then we find the corresponding tangent lines. But that's not really what implicit differentiation is about. This is just kind of a cool tangent that we took to actually explore the derivative and look at the tangent lines in these cases. I think the graph is pretty, at least. But the implicit differentiation part is sort of what we did on paper. So that's our first example. Let's look at some other examples. Oops. That there. I didn't need that or that. All right. And let's look at another example. All right, so I promised you that we would look at the derivations of the derivative of natural log of x, the derivative of log base a of x, and our inverse trig functions. I told you that the rules were 1 over x here and 1 over natural log of a times x, but I didn't give you a reason. In order to find that, we can use implicit differentiation. So let's do that. We know that y is equal to natural log of x, and we want the derivative of y with respect to x. But we don't know what the derivative is yet. So we could take the derivative of both sides with respect to x, and we just get dy dx equals derivative of natural log of x, or of course, but how do I find that? I don't have a rule for that yet. So what I can do is I can get rid of this logarithm and write everything in terms of the exponential by exponentiating both sides. So what I end up with is e to the y is equal to natural log of x. And now I can differentiate implicitly. So we'll differentiate the left-hand side with respect to x. And we'll differentiate the right-hand side with respect to x as well. Oops. E to the natural log of x is just x, sorry. Now the derivative of e to the y with respect to x requires the chain rule. Derivative of e to some power is e to that power times the derivative of the inside. Since y is a function of x, we're going to multiply by dy dx. And that equals the derivative of x, which is just 1. And we want to get dy dx by itself. So we'll divide both sides by e to the y. So you have 1 divided by e to the y is dy dx. But you might ask yourself, well, what is e to the y? Well, it's x. So the derivative of y with respect to x is 1 over x, and y was natural log of x. So that means the derivative of natural log of x is 1 over x. And you'd say, okay, wait, what did we do? Okay, we knew that y was a function of x, and we didn't know the derivative of this. So what we did was we said, okay, I'd like to find the derivative of the natural log of x, but I only know those other derivative rules. The ones involving the exponential functions in particular. Since I know the derivatives of the exponential functions, I exponentiated both sides. And then I was able to take the derivative of this implicitly and able to take the derivative of this directly. And that allowed us to find the derivative of y with respect to x, which allows us to find the derivative of natural log of x in general. So that is our rule, the derivative of natural log of x. We do something similar for log base a of x. Now this one, we could avoid implicit differentiation entirely. If we use this rule, log base a of x is natural log of the numerator divided by natural log of the denominator. That's just the change of base formula. So y prime is equal to the derivative of natural log of x divided by natural log of a. Natural log of a is just a constant. So you get 1 over natural log of a times the derivative of natural log of x. So you get 1 over natural log of a times x as the derivative formula for that. So implicit differentiation was not necessary here. But we could have used implicit differentiation. If we wanted to use implicit differentiation, we could. So we could say, okay, well, we've got this. Y equals log base a of x. And I want to get x by itself, or I want to get rid of this log so that I can take the derivative of both sides. So I can find out what the derivative of y with respect to x is. To get rid of a log base a, we'll exponentiate. We'll say a to the y equals a to the log base a of x. Since these are inverse functions, they undo each other. We just end up with a to the y equals 1, or excuse me, a to the y equals x. And then if we differentiate both sides with respect to x now, you can see where this is going. You get the derivative of a to the y is natural log of the base times a to the y power, where y is a function of x, times the derivative of the inside, which we could just call y prime. That equals 1. And then if we divide by this function, we have y prime equals 1 divided by natural log of a times a to the y. A to the y is equal to x. So we get the same answer. So there are multiple ways that we can derive that formula. Now, regarding your inverse trig functions, we have y equals arcsine of x. Remember what that looks like. Like we're graphing, well, I'll show you in a second. To get rid of the arc sign, we'll take the sine of both sides. So the sine of y is equal to the sine of the arc sine of x. And those two functions are inverses, they undo each other. So we get sine of y equals x. And of course, this is provided that y is in the range of the arcsine graph. So y has to be between -1 and, or actually, y can be any real number. X has to be between -1 and 1. And sine of y has to be between -pi/2 and pi/2, sorry. Because that's the range of the arcsine graph. Now we know that sine of y is equal to x, and we'd like to figure out what the derivative of y is. So we take the derivative of both sides with respect to x. The derivative of sine of a function is cosine of that function. Substitute your function back in, and then multiply by the derivative of the inside by the chain rule. That equals the derivative of x, which is 1. And then solve for y prime. Y prime is 1 divided by cosine of y. We say, okay, well, what is cosine of y? Well, I know that sine of y is equal to x. Let's draw a triangle. my angle is y, sine, it's going to be x over 1. That's opposite over hypotenuse when I draw my triangle. So if the side opposite this angle is x, the hypotenuse is 1. Well, then using the Pythagorean theorem, this squared plus this squared has to equal that squared. So I'll call this a. A squared plus x squared equals 1 squared. And that means a equals 1 minus x squared, or a squared equals 1 minus x squared, which means a equals the positive square root of 1 minus x squared. We're assuming that that's a length. So now we've got this triangle with all the sides labeled. And we want cosine of y. Well, cosine of y is adjacent over hypotenuse. So that's square root of 1 minus x squared divided by 1. So we have 1 divided by that, which simplifies to the square root. And that's our y prime. So the derivative with respect to x of y, which was the arcsine of x, turns out to be this 1 over the square root of 1 minus x squared. Notice that has zeros in the denominator when x equals plus or minus 1. If I actually look at the graph of 1 minus x squared, it looks like this. So I'll only be able to take that positive square root on the interval from -1 to 1. And we're dividing by values that are between 0 and 1 as well. So you've got 1 divided by these proper fractions. So we're going to have numbers that are greater than 1 when we divide. And then as x approaches plus or minus 1, we're going to have infinite limit. They're both going to go to infinity. So we're going to have infinity as x approaches -1 from the right, infinity as x approaches +1 from the left, and then a bunch of positive values in between, the slope of 1 in the middle. When x equals 0, we get a slope of 1 here, which means we have a slope of 1. Now, if you're saying, how did you know what that graph looked like? I was really using the fact that x equals sine of y. It's like you're drawing the sine curve on its side like this. And then we're focused on just that one part. So that where we restricted the original sine graph to the interval from -pi to pi, or excuse me, -pi over 2 to pi over 2, in order to make sure that the resulting graph was actually a function. If we x equals sine of y is not a function. Well, x is a function of y, but y is not a function of x in that case. This curve does not pass the vertical line test. But when I restrict the sine function to -pi over 2 to pi over 2, and then switch the roles of x and y, the resulting curve is 1-to-1. So just based on this, what am I expecting? I'm expecting this is approximately 1.5. So at approximately 1, we're going to have a slope of 1 at x equals 0. Actually, let's make a table of values. X equals 1, it's undefined. Maybe x equals -1/2. We'll look at that. X equals 0, +1/2, and 1. The slope is 1 over this quantity. We have undefined values there and there. And at 0, we get 1 divided by the square root of 1 minus 0 squared. So it's just 1 divided by 1, which is 1. And if x is equal to plus or minus 1/2, this is going to be 1/4. 1 minus 1/4 is 3/4, and then you take the square root. So this is the derivative at plus or minus 1/2. And the square root of 3 does not simplify. Square root of 4 is 2. And then you can take the reciprocal of that. So you have 2 divided by the square root of 3 as the values there. And I'm not actually sure what the numerical approximation of those would be. But we can use a calculator to figure that out. But I'm expecting vertical asymptotes here and here. We're taking 1 and dividing it by a small positive number in each case. So I'm expecting the function values to go to infinity. And I'm expecting symmetry on either side of for either value of x. So I think the graph is just going to look like that. Let's look at the graph online and see if our intuition is consistent, or intuition and our calculations are consistent with the graph on Desmos.com. Okay, so here is the arcsine function. You can actually graph x equals sine of y. That's the whole function for x as a function of y. But notice that that fails the vertical line test. If I draw a vertical line, let's say x equals -1/2, it crosses infinitely many times. So that is not invertible. But if we restrict ourselves to the interval from -π/2 to π/2, at least for our x values, for our y values, then we get the arcsine graph. So notice that they're pretty much the same. They're just here on, well, actually, let's do this. That's the whole graph.
Yes.
And then this is the part that we're interested in. It's giving me a hard time. It doesn't allow me to do that. Okay, so let's get rid of that now. And we're just focused on this. Well, this is the derivative graph. And that's consistent with our expectations. The slope is 1. And then as we approach x equals -1 and x equals +1, the y values on the derivative go to infinity. So that's it. The graph on the computer is consistent with our intuition. The derivation for y equals arctangent of x is very similar. Now we know what that graph looks like.
Hi, sister.
If we look at the tangent graph, which looks like this.
Yeah, we're at the lab. Yeah, if we were happy. Oh, we love it. We love it. We love it. We love the area. Yeah, it's so. Yeah, it's fun. So you'll be here in about 5 minutes.
It repeats infinitely many times from -π/2 to π/2, and then 3π/2, 5π/2, and so on. This function does not have an inverse because it fails the horizontal line test. A horizontal line crosses infinitely many times. But if we restrict ourselves to the interval from -π/2 to π/2, then the restricted tangent function has an inverse. This is y equals tangent of x. So we restrict the domain to -π/2 to π/2, not including the endpoints because those are asymptotes. And then we switch the rules of x and y, and that gives us the inverse tangent function. Since this has vertical asymptotes at -π/2 and π/2, the inverse function will have horizontal asymptotes at -π/2 and π/2. And the graph will look like this. And the question is, well, what's the derivative of that graph? What's the slope? Looks like the slopes approach zero as x goes to positive and negative infinity. If I draw a tangent line, it looks like all the tangents should be positive. Let's figure out what that is. We can do that relatively simply. So we've got y equals the arctangent of x. And that's equivalent to the following. If we take the tangent of both sides, we have tangent of y equals x. And then we're restricting ourselves to the interval where y ranges from negative pi over 2 to pi over 2. And then we differentiate implicitly on both sides. The derivative of tangent of a function of x is secant squared of that function. And then we multiply by the derivative of the inside by the chain rule. And that's equal to 1. And so dy dx turns out to be 1 over secant squared y. So we say to ourselves, well, what's 1 over secant squared y? Well, it's cosine squared y. Say, well, what's cosine of y? Well, in order to figure out what cosine of y is, we're going to draw a triangle. We know that tangent of y is equal to x over 1. So we can draw a right triangle where this angle is y. And we want x divided by 1 to be the ratio of the opposite side to the adjacent side. So when the opposite side is x, the adjacent side is 1. And then this side squared plus this side squared equals the hypotenuse squared. So we'll have 1 plus x squared. We'll take the square root to get that hypotenuse. And then we can find the cosine. Cosine of y, according to this, is adjacent over hypotenuse. So it's 1 divided by the square root of 1 plus x squared. And we're going to take that and square it. So you end up with 1 over 1 plus x squared there as our dy dx. So the derivative of arctangent, that was the original function, is equal to 1 over 1 plus x squared. And we can keep going in this way. We did arcsine, we looked at arctangent. Let's do arcsecant now. Let's say y equals arcsecant of x, and we're interested in the derivative. We don't know the derivative of arcsecant, so we take the secant of both sides. But we don't know the derivative of arcsecant, but we do know the derivative of secant. So we get this. Then we differentiate both sides with respect to x, remembering that y is a function of x. Derivative of secant of y is secant of y times tangent of y times the derivative of the inside. And that's equal to the derivative of x, which is 1. So dy dx equals 1 divided by secant of y times tangent of y. And if you want, you can write that as 1 over secant, which is cosine of y, times 1 over tangent, which is cotangent of y. Now to figure out what those should be, put a y here, and we know that the secant of y was equal to x. Now I'd rather think in terms of cosine, so I'll take the reciprocal of both sides. Cosine of y is equal to 1 over x. So the adjacent side is 1 when the hypotenuse is x units long. And then if I call this side b, 1 squared plus b squared has to equal x squared. So b squared must be x squared minus 1, which means that b equals the square root of x squared plus 1. Or minus 1, excuse me. So we end up with cosine of y, which is 1 over x, times cotangent of x, which is cosine, or cotangent is, you could write it as cosine divided by sine, but you can also write it as adjacent over opposite. I still think in terms of opposite, adjacent, hypotenuse, sine, cosine, and tangent, and then have to take reciprocals every time. So the adjacent side in this case is 1. That's the side next to y, that's not the hypotenuse. And the opposite side is that square root. So that's almost our answer. It turns out that we're going to end up using the absolute value of x here. So we end up with 1 over the absolute value of x, of this absolute value of x, excuse me, times the square root of x squared minus 1 as the derivative of arcsec. And that's just because of some domain and range issues involving the arcsecant function. I said derivative of arcsine, but I meant derivative of arcsecant. All right, now if we want to, we can explore these graphs, graph this and show that this should be, this is the appropriate slope function for that function. And we can do the same thing with this one. We can graph this function and show that that's the appropriate slope for this function as well. Now this one, 1 over 1 plus x squared, is something I can probably graph by hand. When x is equal to 0, we get 1. So if this is pi over 2, which is about 1.5, I'm going to get about 1 right here. Well, I'm going to get exactly 1 right here. It's about 2/3 of the way to 1.5, right? And then as x goes to plus or minus infinity, the function's going to approach 0. So we see that symmetry on the left and right, which makes sense because if I replace x with negative x, I get the same function. And I also have a maximum of at x equals 0. And as x increases, the denominator gets larger and larger, so the fraction gets smaller. So what this indicates is that the slope of the arctangent of x is always positive. It has a maximum value of 1 in the middle. And I think that's consistent with our expectations, with just our intuition. If I draw any tangent lines along the curve, every time I draw a tangent line, they're sloping up. As you go from left to right, they're increasing. So the slopes are all positive numbers. Now they're much less steep over here. They're close to 0, but they're small positive slopes. So I would expect the values of the derivative to be near 0. And the same is true over on this end. As we get close to y equals pi over 2, we have lines with a small positive slope, but their slope is close to 0. So we end up with derivative values that look something like this graph. And that's y prime equals 1 over 1 plus x squared. This one is a little less obvious, but you can tell a couple of things about the derivative. X equals 0, x equals 1, and x equals -1 are vertical asymptotes. Because that function is undefined at those values. And what else should we say? This is always a positive number, this is always a positive number, so these are always positive. X squared minus 1 looks like this. So this is only going to be well defined for x from -infinity to -1 and 1 to infinity. When x is in between -1 and 1, this expression is the square root of a negative number, which is undefined. Might also be helpful to look at the graph of the arcsecant of x. So to graph arcsecant, we would graph cosine first, which looks like this. And the secant function can be found by first finding the vertical asymptotes of secant. Whenever cosine is 1, secant is 1. Whenever cosine is -1, secant is -1. When as cosine approaches 0 and it's a tiny positive number, we're gonna get a large positive number. So I get branches like this. As cosine approaches 0 and it's a tiny negative number, we're gonna have branches like that. And then it repeats over and over again. So this blue graph is the secant graph, but it does not have a what's it called, an inverse as it is, because if I draw a horizontal line, that horizontal line is going to cross infinitely many times. This fails the horizontal line test. We need to restrict ourselves to an interval. Now with the cosine graph, we tend to restrict ourselves to the interval from 0 to pi. We do the same thing for the secant. So we're going to look at the interval from 0 to pi, which means we're looking at those two branches. So that's what we're interested in. So when I switch the roles of x and y now, my graph will only exist from -infinity to -1 and +1 to infinity. We've got this horizontal asymptote at y equals +pi/2. And the graph will look like this. This is the point x equals x equals pi, y equals -1. So we switch the rules of x and y, we get that point. And then it approaches that asymptote. This one approaches the vertical line at x equals -pi/2, or excuse me, +pi/2, and this one approaches the horizontal line y equals pi/2. We're really just like looking at this graph sideways and then flipping. And that's how I'm getting this graph. All right, with that in mind, I made a mistake here. X equals 0 can't be a vertical asymptote because x equals 0 is not even in the domain. We're only going to substitute x values between -infinity and -1, and positive, or x equals 1 and infinity. But we'll have a vertical asymptote there and a vertical asymptote there. And all of these slopes are positive. They get less positive. So they are initially very steep and then they approach 0. I think that derivative might look like that. And here, these slopes are all negative. But those slopes approach 0 as well. So I'm expecting that part of the graph to look like that. So I've got this branch and this branch for my derivative graph. I'm actually not sure what this looks like because I've never graphed this before. Let's graph this on Desmos.com. Yes. So this was the arcsine graph. Let's graph arcsecant. There's arcsecant. Let's graph that horizontal asymptote. If that's consistent with our expectations. And then let's graph y prime equals the 1 divided by the absolute value of x times the square root of x squared minus 1. And that's consistent, almost consistent with my expectations. Oh, do. There's actually symmetry. This side I got right and this side I got wrong. Tangent lines over here have an increasing, or have a positive slope. The tangent lines are increasing. I said that they were decreasing. I don't know why I said that they were decreasing. If I graph a tangent line on this side, the tangent lines go up as you look at them from left to right. So this actually is the appropriate graph and there is symmetry. So let's see. I think that's what we want. This green graph is the derivative of this graph here. Now we're not going to do the derivations for arc cosine, arc cotangent, arc cosecant, but you can imagine how they're going to be very similar. If I have a cosine here instead of an arc cosine instead of an arc sine, I'm going to take the cosine of both sides. And when I take the derivative of cosine, I'm going to get a negative sine value. So that's going to give me an extra factor of -1. After you do the calculations for arc cosine, you get a derivative that looks very similar to this. It just has a -1 in the numerator. That -1 comes from the fact that the derivative of cosine is negative. When you look at the version of this for arc cotangent, it's the same thing. The derivative of cotangent of x is negative cosecant squared x. So the procedure is going to be very similar to this, but you're going to have this extra factor of -1 that comes from the fact that cofunctions have negative derivatives. The same thing with the arc cosecant. The derivative of cosecant is negative cosecant cotangent. So after you take the secant of both sides and take the derivatives implicitly, you're going to end up with this negative factor, which just changes the sign in the numerator. So you got these 3 rules, but they actually correspond to 6 rules. Just turn those functions to the corresponding cofunctions and multiply the numerators by -1, and you'll have the resulting derivatives. But all of them can be found using implicit differentiation, which is just the chain rule, essentially. So that's it for implicit differentiation. Let me know if you have any questions about that. Be careful about using those derivative formulas that you find using implicit differentiation. Remember, you have to plug in points that are actually on the graph in order for the answer to make sense.